Hello, so I want to go over this press release, which is physicists find misaligned carbon sheets yield unparalleled properties. So let's just jump into it, but right now we are talking about carbon nanosheets. So these are these carbon atoms that are aligned in a two-dimensional structure, hexagonal structure to be explicit, and when you lay two of these on top of each other, or if you lay one on top of a different one, then you can end up having very peculiar chemical properties that emerge out of the system. So without further ado, a material composed of two 1-atom-thick layers of carbon has grabbed the attention of physicists worldwide for its intriguing and potentially exploitable conductive properties. So you might have heard that carbon nanosheets or carbon graphene sheets, these are going to be beneficial for the electronics industry because there is very, very low chemical conductance, or I should say there's very high chemical conductance and there's very low electrical resistance of these particular materials. So anyways, and this is going along with the sheet or along the graphene, not across it. Anyways, Dr. Fan Zhang, assistant professor of physics in the School of Natural Sciences and Mathematics at the University of Texas at Dallas, the physics doctoral student, and I apologize for mispronouncing this name, but Shiwei Wing published an article in June with Dr. Fengnian Chia's group at Yale University in Nature Photonics that describes how the ability of twisted bilayer graphene to conduct electrical current changes in response to mid-infrared light. Okay, so mid-infrared light, this is just a particular wavelength or a series of wavelengths of light that are the wavelength is too long for you to see it, but you can feel it very easily. So graphene is a single layer of carbon atoms arranged in a flat honeycomb pattern where each hexagon is formed by 6 carbon atoms at its vertices. Since graphene's first isolation in 2004, its unique properties have been intensely studied by scientists for potential use in advanced computers, materials, and devices. So if two sheets of graphene are stacked on top of one another and one layer is rotated so that the layers are slightly out of alignment, the resulting physical configuration called twisted bilayer graphene yields electronic properties that differ significantly from those exhibited by a single layer alone or by two aligned layers. Yeah, that is a tongue twister for me, single layer. Anyways, graphene has been of interest for about 15 years, Zhang said. A single layer is interesting to study, but if we have two layers, their interactions should render much richer and more interesting physics. And this is why we want to study bilayer graphene systems. Okay? So this is a new field. So when the graphene layers are misaligned, a new periodic design in the mesh emerges called a Moire pattern. And I don't speak French, but I don't know if I'm not pronouncing that correctly. So the Moire pattern is also a hexagon, but it can be made up of more than 10,000 carbon atoms. Yeah. So rather than making a hexagon with 6 atoms, we are making hexagons with over 10,000 carbon atoms. Okay. So the angle at which the two layers of graphene are misaligned, the twist angle, is critically important to the material's electronic properties, Wing said. The smaller the twist angle, the larger the Moire periodicity. And the periodicity would be the single unit, right? So here, with our single layer of graphene, our periodicity are these 6 carbon atom units, right? But if you twist it, you can create other hexagons or you can create other shapes that are much larger if that misalignment is a smaller angle. So with that, I want to direct our attention to what a Moire pattern actually is, and you probably have seen it in mosquito nets or screens very frequently when you have two screens or two repeating patterns that line up on top of each other and they're misaligned just slightly. This would be, you can see these patterns easily in nature. So here we have one sheet, and then by putting another sheet of the same pattern, or you know what, it might even be a different pattern, you can create these very complex shapes. And notice, when he has the screen directly on top, the periodicity is very large. But as he twists it and increases the angle in between the screens, then the periodicity shrinks and shrinks, and then you can get much more complicated patterns. So here, let me get this up again. So here, you can see as they are lined up very well, it's very hard to see periodicity because the individual unit is so large. But as he twists it more and more, you can see more of these squares that are appearing as he twists it more. And so this is the same concept that these people were talking about with these graphene layers. These graphene layers have these hexagonal patterns and a single bilayer, but if you twist them slightly, you can create different hexagonal patterns. And granted, there might be even more, what would the word be? There might be other shapes that you could generate through particular mismatching, but just so you know, this is what we are experiencing right now. So let's say the unusual effects of a specific twist. The unusual effects of a specific twist angles on electron behavior were first proposed in 2011 article by Dr. Alan McDonald, professor of physics at UT Austin, and Dr. Rafi Bistritzner. Jang witnessed the birth of this field as a doctoral student at McDonald's group. So at the time, others really paid no attention to the theory, but now it has become arguably the hottest topic in physics, Jang said. And you know what? I feel like anyone who's doing their postdoctoral research on a particular field, there's kind of a vested interest or a conflict of interest to say that they are dealing with the most or the hottest topic in their particular field. Regardless, we can move on from that. So in 2011 research, McDonald and Bistritzner predicted that electrons' kinetic energy can vanish in a graphene bilayer misaligned by the so-called magic angle of 1.1 degrees. And so in 2018, researchers at the Massachusetts MIT proved this theory, finding that offsetting the two graphene layers by 1.1 degrees produced a two-dimensional superconductor, a material that conducts electrical current with no resistance and no energy loss. So here's another example of, if we have two of these graphene layers on top of each other and you twist them just right, you can see that you have emerging hexagonal patterns coming from the two layered on top of each other. So that is what you can experience, and here they're talking about the twist angle, and if this angle is 1.1 degrees, then, so this is way too high, so 1.1 degrees is going to be minuscule, and thus you're going to have very large hexagons that are much larger than what you see right here. But if this angle is 1.1, then we are creating a superconductor that is basically lossless energy. So you are able to transfer, I shouldn't say lossless energy, I should say there is lossless conduction. So there is no heat that is generated when an electron flows through that particular material. And granted, there's a limit to how much current can flow before the superconductivity breaks down, but at least for the currents that they were using in their study, lossless transfer of energy, right? Anyways, in a 2019 article in Science Advances, Zhang and Wang, together with Dr. Jeannie Lau's group at the OSU, showed that when offset by 0.93 degrees, the twisted bilayer graphene exhibits both superconducting and insulating states. So this is very, very promising, because if something can be both a superconductor and insulating, there might be uses for it in electronics as far as microchips go, and as far as data storage goes. So as you might be aware, semiconductors are used often in the microchips or the data collection, or sorry, data storage field, because they can be in different states. So they can be in one state where there is no electrical current flowing through them, and they can exist in an on state where the electrical current is flowing through them, and that's how you get your bits, right? You get your zeros and ones as a result of that. So what is nice about this particular arrangement, and the reason why semiconductors are used is because it requires some energy to kick it from one state into another, right? And so you're able to switch them off and on to not be flowing electricity or to be flowing electricity. The great thing about this, what I'm seeing, is that you could have both an this is functioning very similarly to a semiconductor in that it can have both an off and an on state. So let's continue. So what I would say is if there is a way to turn this off and on, you could probably see this being used as a much more efficient and a much, what would the word be, a much better material to use in microchip creation. So in our previous work, we saw, okay, I said that already. Oh yeah, in our previous work, we saw superconductivity as well as insulation. That's what's making the study of twisted bilayer graphene such a hot field, superconductivity. The fact that you can manipulate pure carbon to superconduct is amazing and unprecedented, Wang said. So, in his most recent research in Nature Photonics, Zheng and his collaborators at Yale investigated whether and how twisted bilayer graphene interacts with mid-infrared light, which humans can't see but can detect as heat. So interactions between light and matter are useful in many devices. For example, converting sunlight into electrical power, and almost every object emits infrared light, including people, and this light can be detected with devices. So Zheng is a theoretical physicist, so he and Wang set out to determine how mid-infrared light might affect the conductance of electrons in twisted bilayer graphene. The work involved calculating the light absorption based on the Moire pattern band structure. So just know that they were able to probably do some computer modeling with this Moire pattern band structure, and then they could calculate the absorption or how this particular pattern would absorb these particular wavelengths of light. And this is a concept, that determines how electrons move in a material quantum mechanically. So graphene has been of interest for about 15 years. A single layer is interesting to study, but if we have two layers, their interaction could render much richer, more interesting physics. This is why we want to study bilayer graphene systems. So there are standard ways to calculate the band structure and light absorption in a regular crystal, but this is an artificial crystal, so we had to come up with a new method. So using resources at Texas Advanced Computing Center, a supercomputer facility on the UT Austin campus, Wang calculated the band structure and showed how the materials absorbed light. So the Yale group fabricated devices and ran experiments showing the mid-infrared photoresponse. The increase in conductance due to light shining was unusually strong and largest at a twist angle of 1.8 degrees. So the strong photoresponse vanished for a twist angle less than 0.5 degrees. So our theoretical results not only matched well with the experimental findings, but also pointed to a mechanism that is fundamentally connected to the period of Moire pattern, which itself is connected to the twist angle between the two graphene layers. Interesting. So what I'm understanding here is they were shining this light on the different angles of graphene, and they were basically twisting the graphene and seeing how it is interacting with the light. And there were a lot specific angles that basically would turn off the conductance. So what it sounds like is that the light is hitting the graphene sheets and then knocking electrons out, and then these electrons, if they're in a superconducting material, will basically move, and then you can detect those moving electrons. However, if they are in an insulating environment, they can't move, right? Because the material is not made, or the material does not have the properties that allow for the electrons to move and be detected in that particular way. So as a result, they're saying, yes, you can have certain angles where you do have conductance and certain angles where you have insulation. And this could be very, very beneficial for creating a wide variety of new materials with very variable electronic properties. So the next step. So the twist angle is clearly very important in determining the properties of twisted bilayer graphene. The question arises, can we apply this to tune other two-dimensional materials to get unprecedented features? So this is not dealing just with graphene. There are a lot of crystals in nature, many crystals in nature, that might also have very similar properties if we are able to manipulate them properly. So can we combine the photoresponse and the superconductivity of in twisted bilayer graphene? For example, can shining a light induce or somehow modulate superconductivity? That will be very interesting to study. So this shining of a light to modulate superconductivity, this would be theoretically a way that you could encode for information on a particular device. So this new breakthrough will potentially enable a new class of infrared detectors based on graphene with high sensitivity. Oh, and look, this is an element of the U.S. Army Combat Compatibilities Development Command Army Research Laboratory, so there might be some defense-related research involved with this as well. So these new detectors will potentially impact applications such as night vision, which is of critical importance for the U.S. Army. So I think that this is interesting, and I think it would be very interesting to see if there would be ways that you can combine two of these graphene units, and let's say that you are able to take these two sheets, and they might not even have to be very large. But let's say you have two sheets, and let's say you chemically modify the surrounding material. Now, let's say, is it possible that you could chemically modify it so that under certain temperatures that it could twist more or less? I think that would be an extremely interesting field, because if you could say modulate the angle, I should hold them. If you could modulate the angle using chemical modifications on the perimeter of your carbon nanosheets, or your graphene sheets, that would be really an effective and efficient way to study these unique chemical properties. And you might be able to create materials that will change the chemical properties based on their environment or based on their surroundings. So I really like this. This would be a way to sort of create or recreate, a homeostatic system in some way. So yeah, I find this very interesting, and I hope you do too. And I will leave the citations in the what's it called? Not the comments, in the description if you want to read this for yourself. So thanks for coming to this, and hopefully I will see you later today.